So the other day we started discussing the ideal gas law. And what that basically does is it allows us to solve for pressure, volume, moles or amount of gas, or temperature. And all that can be done because of a thing called a gas constant. So let's take a look at that for a moment. These are not needed to be memorized, but what you need to understand is the gas constant is a relationship of my pressure, my volume, my moles, and my temperature. This is just a rearrangement of this. So here are three different values, and you'll notice this is a pressure, this is a volume, that's my moles, and this is my temperature. If it's an ATM, that's that value, if I have kPa, or if I have torr. Please note that the only difference is my pressure. So you do not need to write this down, just visually see this. If I look at a problem, such as this, it says what is the volume of 1 mole, so that's my N, here's my V, nitrogen gas sample that is found at a temperature, 0 degrees Celsius, and 760 torr. Okay, so I'm solving for volume, so I rearrange this, and it'll be V equals nRT over P. So I plug in my numbers, there's my mole, right? My R value I'll discuss in a second. Here's 273 because I need Kelvin, and then 760 torr. Because I'm in torr, I need to use this R value. I will go back quickly. My R value for torr is 62.4. So that's why I need 62.4 for my R value. I multiply and divide, and I get 22.4 liters. And what that actually is doing is showing the fact that this is actually at STP if you didn't realize it. 760 torr is 1 ATM. 1 ATM in 0 degrees, when you have 1 mole of it, equals 22.4 liters. So that's how that's always going to come out. All right. But there is a derivative. I do want you to do this on the back of your sheet. You can just do the problem if you want. This is relating to, I believe, number 18 and 19 on our worksheet that you just got on Monday. So it says, what is the density of chlorine gas at 25 degrees and 0.98 ATM? Okay, so don't need to write this down yet, but if you have PV equals nRT, let me just show you where this comes from. Moles is actually mass over molar mass, how much it weighs in 1 mole. And then I kind of change that around, and voila, please write this down right here. You have molar mass, big M, equals dRT, density times their constant, times T over P. Or I like to say, because we are not barbarians, we will always cover our dirt, or use the dirt to cover our P. So dirt always covers your P, obviously, right? So it's dirt over P equals molar mass, okay? So let's talk about how I would do this equation. I'm going to use this equation here. So I am solving for density, so I'm solving for the D. So molar mass, where do I get molar masses from? The periodic table. Molar mass chlorine is Cl2. It is a diatomic. So 35.45 plus 35.45 from the periodic table is 70.9 grams per mole. I don't know D. What's my R? Whatever the ATM is. That's the 0.0821 because of ATM. What's my T? 25 plus 273. And then what's my P? There's the 0.98. Okay, so you can be doing densities, or you can find molar masses by using dirt over P. And then my answer would be 2.84, and it's grams per liter because the grams and the liters do not cancel out. If you just memorize that density is grams per liters, that's just as easy. Okay, I know we have a short mod, so I apologize, but we need to do these 3 problems that are on your note sheet now. So, gas stoichiometry. It is just like normal stoichiometry. If you struggled in stoichiometry, you have yet another opportunity to try to hammer this down. Okay, so we have a little flow chart on the top. It should look very familiar to you. Right, we can fill this in quickly. You can just do the first letters if you want, but you got grams, moles, and particles, right? And then we'd have grams, moles, and particles. And in the middle, I suggest you not writing these down for now, unless if you can keep up. In between these, we'd always use molar mass. And in between these, we'd always do Avogadro's number. Well, you'll notice on the note sheet, there is a new player on the bottom, and that is going to be liters. And those liters are very special because they only happen at certain times. Please make sure you write this down on the arrow. It is at STP, then it's 22.4 liters. You are only allowed on that road, on that path, between liters and moles if you're at STP. Okay, So let's take a look at our first problem. We're going to talk about combusting of propane, which is from a gas grill. We don't have time to watch this video right now. It's more of a news program on safety anyway. So let's take a look at this. It says, how many liters of CO2 are produced when 54.2 grams of propane reacts with excess O2 at STP? Well, let me show you what this means. I highlighted this. I want to know how many liters from grams. So a lot of you, if you look at that right now, check it out. 1, 2, 3, right? I just have to get through that. Notice how I organize my information. I'd suggest you do the same. I have 54.2 grams. So I'd write that right there. What do? I need to go in between here. Units always go on the bottom, right? So there's my 44 grams. It's 12 times 3 plus 8. What goes on top? 1 mole. Now I'm here. What happens next? Mole ratio. I have a 3. I have a 1. That should make a lot of sense. Nothing's new yet. From here to here, that's not new. All is new is this. I got to get from moles to liters. So moles would go on the bottom, right? And what number do I use? If you have 1 mole, you have 22.4 liters. And that's it. You multiply the top, you divide the bottom, and you get 82.8 liters of CO2. So that is using our normal flow chart, and we just call it gas stoichiometry because you're utilizing the liters. Okay? Let's go to the next problem, if we could. Same exact equation. This time it says what mass of CO2 is produced if I have C3H8 reacts at this pressure and a temperature in a volume. So I have P, I have T, and I have V. How does that work? This is not at STP, right? I would need 101.3, and I would need 0 degrees Celsius. That is not the case. So let me show you what we would do if we're not at STP. So I can't go through this path, okay? You can't do it. Don't cross yours out. Just know you can't. So if I want to go from here all the way up here, but I can't go through it because I'm at STP, the road is closed. So I have to take a detour. So you have those lines on your sheet. So notice this detour gets you to moles. What's moles? Moles is N. So all I need is this equation. So please write that on your flow chart on the left. N equals PV over RT. If I plug in a P, a V, and a T, and I always know an R, I can hop this, take this detour, and now I'm in the game. Now I can just go from here to here. Okay? So we're going to do it through the detour. So I have organized my information, all right? And what I'm going to do first, start this way to the left of your paper, is I'm going to do moles of my C3H8 equaling the PV over the RT. So I just plug and play, you guys. 98.2 kPa, 0.95 liters, right? It's got to be in liters. I'm using 8.314 R because that's the R value that corresponds to kPa. And then that's my temperature. 273 plus 21 is 294. I get that value of 0.0382 moles of propane. Okay, now I'm in moles. Now, how many steps is that to get the grams? 2, right? 1, 2. So I start with that then. So I already have my ideal gas law. You can literally just put this underneath the answer. Yeah, you don't even have to start a new area. This is just in the same line. So now what am I doing? Mole ratio. I'm going to this. That's a 3. I'm coming from the 1. So there's 1 to 3. And then I want to go up to here. I've circled that. So I bring moles down, right? 1 mole. And then I need to look up the mass of what? CO2. And CO2 is 12 plus 16 plus 16, 44 grams. So multiply, multiply. 5.04 grams of CO2. Okay, so if you're not at STP, you got to utilize the ideal gas law. And this will always be the same on this side. You are skipping this to moles, so you know you have to solve for N. Every time you're solving for N. All right, let's look at the last scenario, and we are done. So the last one I have, if I have that many particles that react, how many liters of carbon dioxide would be produced at these conditions? Again, not at STP. I would need 760 torr, which is 1 ATM, and 0 degrees. So if I want to start here, and I'm ending at liters down here, I got to go through here, through that way, and through this way. But what's the rule? I can only go through this in STP. So my road is closed again. So I need to take another detour. So I can get this far, but now I can't go through this way. So what do I need to do? I need to use the ideal gas law. And what is this? VP, T, or N? The liters are V. So I would solve for V. Because you have N, that's going to go right there. You're going to be given T and P. You plug it in, you get to liters. Let's take a look. So I have this many particles, and I have this information about my CO2. Let me show you how I use it. So first, particles. Boom, there it is. 4.52 times 10 to the 23rd particles of O2. If I want to go through this path right now, what do I have to use? Avogadro's number. So 6.02 times 10 to the 23rd. What goes on top? I'm going to moles. That's 1. Now where am I? Now I got to go through here. Mole ratio. I have 5 and I have a 3. So the 5 goes on the bottom because I have O2 first. And the 3 goes on the top because that's what I'm trying to find. And I can't go any further. So that is my moles. Okay. 0.4503 moles of CO2. We're going to take that number. Okay. We have N now. That's my N. We have a P right here. We have a T. So I can plug those 3 things in, N, T, and P, and I can solve for N, or V. So that's my N. That's my P. That's my T. So now I plug it in, and I label it like this. So there's my N right here. There's my T, 273 plus 30, and there's my P. And why am I using 62.4? Because it's in torr. So I have to use that one. If it was ATM, I'd use 0.0821. If it was KPA, I'd use 8.314. I multiply, I divide, and I get my final answer of 11.82 liters of CO2. So it is really about the flow chart. We will be practicing this a lot, but you can start working at that on your worksheet. And on Friday, tomorrow, we will be going through that in quite detailed fashion.